My name is Wennyk, and we're going to be learning all about UL 1973 certification for stacks. So hopefully it's not too dry, and there'll be sections in here that'll be relevant for most of you that are listening in. So welcome back for those of you that were joined in tutorial 1, where we learned about the optimal design approaches for battery racking and packs and modules. This is tutorial 2, so we're going to be looking at battery stack designs when it as it pertains to UL 1973 certification. So we will be starting with a brief introduction of who we are. I'll explain the common battery stack architectures, defining terms that we'll be using throughout the discussion today. We'll explore the impact component certifications have on the level of effort to complete a UL 1973 certification. I'll also share our experiences working with nationally recognized test labs through that process. And I'll finish this webinar with a discussion of how it's possible and also pretty desirable to design in flexibility for these locked down stack configurations. So our headquarter office is located in Sunnyvale, California. We have a design center located in Waterloo, Canada, and that is where I'm based. Our electronic product design division was founded in 1997. Over the years, we've introduced our battery management solutions for high voltage and low voltage battery stacks, as well as our battery control panel for managing parallel arrangements of battery stacks, normally geared for large energy storage systems. And more recently, we've brought out an EMS solution for sites that need help managing various other assets. We also offer design engineering and system integration support. And it's through that integration support that I found myself sometimes, supporting remote islands in the middle of the Pacific. Our BMS recently received UL recognition for UL 1973 by completing both UL 991 and 1998. Our BMS is the first world's configurable BMS for recognition under UL 1973. And so what I mean by configurable is that it's configured to work with different chemistries, different battery manufacturers, different stack voltages and topologies without having to reopen any of the UL 991 or 1998 reports. And UL actually didn't have a process for completing functional safety of a configurable BMS in this way. And so now that we've achieved that, this BMS cuts the UL 1973 certification time in half and reduces cost. And this is an updated map of all of our systems in the field. It's kind of nice to hear that there's people joining on the call from all 6 continents, because we've recently deployed to Africa and South America, thus completing our deployments to every continent, apart from Antarctica. We're still waiting on that weather research station opportunity to get in there. So with that sort of introduction of who we are, I'm going to just go into battery stack architectures and kind of lay the groundwork for definitions that we'll be using throughout the webinar today. So to start things off, this is our product lineup for protecting these cells throughout various stages. So we've got the cell interface module, and that's at the module level. And so it passes specific information to the stack switchgear, as well as performing the cell balancing routines. The stack switchgear, which goes in a rack, will handle the high current electrical connection between the stack and the outside system. So whether that's a shared DC bus or the inverter or any other system that's needing to make use of the battery. And that's also where stack level fusing and contactors are located. And our battery control panel, which is relatively a new release for us, it intelligently manages these multiple stacks that are connected to a parallel common DC bus. So they allow large ESS systems to be put together without having to code up and verify how the different stacks interoperate. So to begin, we're going to start at the beginning, like all good things. And so I'm going to be defining terms like cells, modules, racks, and stacks, because I want to make sure that we all have the same understanding as we go through the presentation. So in this webinar, a cell is going to be referring to the smallest unit of electrochemical energy storage that's distinguishable by like a pouch or a cylindrical or like a prismatic shape. As part of UL 1973, the single cell failure test, that failure would be produced in that single cell. One cell, as defined by the perspective of the BMS, may consist of multiple electrical chemical cells in parallel. So for example, we're all familiar with the terms of 2S, 2P, or the S and the Ps. So a 1P cell would be a single electrochemical cell, whereas like a 2P would be two of those connected in parallel. And from the perspective of the BMS, they appear as a single cell and just with twice the capacity. But for UL 1973, the cell is referring to the electrochemical pouch. And so when we assemble those into a module, UL 1973 recognizes a module as a mechanical subassembly. And so that will also contain among the cells a frame, and that frame can hold the cells, but it also offers some flame and heat barrier, which is important for managing thermal propagation. We can also have the thermal conduction channels in place. So those would be things like heat sinks, chiller plates, air corridors for forced air cooling. It'll also have the cell-to-cell interconnects for how to wire the high current path, as well as they usually integrate the temperature sensors right inside the module. And those modules are then put onto a tray, and because we need some sort of way to hold them. And that tray can either be permanently mounted or it can be affixed with sliders. And that sort of decision comes down to installation and maintenance. And the installation and maintenance plan is actually reviewed as part of 1973. So that's like requirement 42. And so to design this properly, we're looking at a tray that is considering weight, the working area around it, and the type of maintenance operations that could be carried out. So if we were, every year or so retorquing high current connections, well, a slider would be more appealing than a permanently mounted tray. And so we got these trays now. So trays are installed in a rack. That's kind of like the next level up. And multiple racks can be part of a stack. So if we were to connect all of these modules that are inside a single rack in series, and then place a few more racks beside it and wire those in series, and that's all managed by a stack switchgear, that's considered a stack. In UL 1973, this is what they refer to as a battery stack. And the battery stack is also contained within a protective enclosure to provide mechanical protection from impacts, but also to impede fire propagation. And I should pause a little bit on this third bullet, was specific around fire propagation, because that is a test that's carried out as part of UL 1973. Most of us in the US are familiar with the International Fire Code and the NFPA regulations that depending on the size of the battery stack, you may have to go through a UL 9540A large scale fire testing. But UL 1973 also carries out a test where they will observe fire propagation within a given battery stack, and they're checking to make sure that there's no flame propagation, so there's no flames coming out or an explosion. So the design of that enclosure actually is important when it comes to a 1973 system. And of course, the battery stack can also consist of thermal management. So those would be things like fans, liquid reservoirs, air ducting. You can get pretty integrated, as well as the protection devices. So as mentioned, the stack switchgear will have fuses and contactors, and that's what I'm referring to. And so this image is actually one of our configurable stacks that was designed for a customer. So it was giving them the options to remove or add modules and racks to a stack to reconfigure it for different voltages. And I should also point out, though, because not all, just as all cells come in different shapes and sizes, that also translates to a battery stack. So for very large format cells, they don't really fit the mold of the definition of a module tray, those types of words, and that's okay. It's especially, these large cells are pretty heavy, so you're pretty much dealing with them on their own. But this type of design is still valid within the requirements of 1973. It's just going to present additional challenges. So for instance, the single cell failure propagation might be a little bit more difficult to design in. So let's dive into what it means to have a UL 1973 recognized or certified battery stack. And just carrying over from tutorial 1, because we briefly introduced this concept, a high-level ESS would be evaluated to 9540, and as a result, those battery stacks that's in there would have to be evaluated to 1973 as well. So a 1973 certified stack, if you already had that, would just check the box. So if you were to submit for a UL 9540 evaluation, what that would look like is they would get to this section, they would see that you're using a 1973 certified stack, and they would check the box. So that reduces a lot of test time and cost because you don't have to go through that with the stack that you brought. And so as we can already see from this simple diagram, there's a hierarchical approach when it comes to these types of standards. And so 9540 will call out 1741 for power conversion systems and 1973 for stacks. And so the chain doesn't really end here. It keeps going. So for a UL 1973 certification, there's a construction review and a performance testing of the battery stack. So as mentioned in tutorial 1, there are 2 additional standards of interest which are applicable to a BMS, those being UL 991, which pertains to the hardware, and 1998, which pertains to the software. And they're quite involved standards. So, UL 991 requires a full analysis, both failure mode effect analysis as well as testing. And for 1998, that's a very, very detailed software and coding review, looking at both the code itself, but also how you test it to make sure that there's no code regressions that can get in there. But by using a BMS that's already UL recognized, that checks the box. So you can kind of skip over this large schedule and cost hit and just move up to the higher level. And it doesn't really end with BMS components. In fact, as part of 1973 requirement 2.1, it's saying that all components used as part of the stack have to comply with the components, the requirements for that component. So to list a few of these, it's not an extensive list by any means. There's a lot more than this. But like lithium cells for 1642, we've got fuses. So that's like the CSA spec or the UL spec for 248, bands for 507, and it just goes on. So any component shall comply with the CSA, UL, or ULC standards appropriate for where the country is, the product's used. And uncertified or unrecognized components will be evaluated to the respective standard. And it's that last point here that's the really sticking point when it comes to a 1973 battery stack. So if you can imagine for a moment as a project manager responsible for certification budgets and schedules of a battery stack, it can come as a shock to discover that the engineering team selected components that now must go through additional testing or end up being substituted out for certified or recognized components. And it's rare to find a drop-in certified or recognized component, and sometimes that component just simply doesn't exist. So when setting out on the road for a UL 1973 certification, it's very important that the design team at its lowest level is aware of this high level requirement, so correct components can be used from day one. And speaking of correct components, our low voltage BMS and high voltage BMSs are recognized. There's a UL file number if you wanted to look it up in the IQ UL database. Our high voltage stack switchgear product is currently under review. So we've got that review ongoing with UL at this moment. And so within the stack switchgear, we would find the fuses and contactors, which are part of the list on that previous slide. And in this case, we would be getting them recognized as part of our process. So the stack switchgear can save a lot of that effort of a lot of those critical and deeper parts. And certain UL 1973 prescribed tests are just guaranteed to pass when using a certified component. And I'm going to be talking about that over the next couple slides to show how using the certified components reduces the risk of a roadblock. Because any sort of non-compliant result can delay the schedule here. And so by using the certified components, you're minimizing your project's risk of not completing on time. So one part of UL 1973 is the overcharge test. So this is a test that applies a current to the battery stack with a single fault condition applied. So this is after a construction review has been completed of your 1973 stack, the NRTL reviewer has an idea of where a weakness might lie and where is the best place to put that single point failure. So they may bypass your contactor or just remove power from the BMS. And then they're going to apply the charging process. And ideally, your protective circuitry isn't compromised by a single point failure, so the charging process is just terminated. However, you know, if that doesn't happen, it's a pretty spectacular test. If a cell is prone to being damaged from overcharge. So with a properly configured and recognized BMS, the test passes every time. And honestly, it's downright boring to watch. We just go through the process, you know, install a jumper across one of the contactors or whatever their single point failure might be. They run the test, the system works as designed, and you just move on to the next electrical test. And the same thing works for over discharge as well, just in the opposite direction, because you're starting with a fully charged stack and discharging till empty. There's also a charge and balance test. And this test begins with a fully discharged stack except a single cell that is half full. And that stack is then charged in a typical manner for the end application. So again, the ideal charging process is terminated by the recognized component before that single cell exceeds the cell's manufacturing limit. But this can be kind of hard to understand how this test works. So I've also got a visualization for the next couple slides just to help articulate what this is. So this specific test, this charge and balance test, has caught a lot of lead acid stack designers off guard. In addition to looking for thermal runaway conditions, the NRTL reviewer is also going to be looking for gases which an overcharged lead acid cell may produce. If we think back to the early lead acid systems used in telecommunication stations and UPS applications, it was pretty uncommon to see a BMS attached to that stack, monitoring each individual cell. Instead, the intention was given to manage the room. So you're evacuating any unwanted gases with proper ventilation and having sensors to set off alarms when the concentration becomes too large. But UL 1973 sets out a limit for that concentration of gas that can be generated from the stack. And so we're seeing a lot of new systems that require BMS to protect their stack against that. And so the key takeaway here is that without a BMS, the PCS is determining the charge limit based on stack voltage, which is kind of assuming the average of individual cell voltages. And so that can miss the high cell by the time the average reaches the full mark. And at that point, that cell can become overcharged and can vent. And so then since the BMS is monitoring each individual cell, it knows when that cell is reaching full and can avert the charge current. So the trip, it basically just trips and opens the high current path before any outgassing can occur. So this takes a test that potentially could fail or lead to an undesirable result. And it just, again, it makes it so it's kind of boring. You know that this is that this test will pass. And this safety, or the ability to detect individual cells and limit the or disconnect the stack, it's not necessarily a new concept to those that are in the lithium environment, where the individual cells being volatile and getting out of balance is just a fact of life that we're learning to deal with and manage safely. But for a lot of these industries that have been around for a while, they're used to solving the problem in a different way. And so with UL 1973 coming out, it's now requiring a certain level of stack performance that just hasn't been seen before. And another test I wanted to talk about is a short circuit test. So included in the short circuit test is this concept of a soft short test, where 85 to 100% of the rating is applied. So this is the nameplate rating of a fuse. And so it's not necessarily intuitive that a fuse can't be used to meet a short circuit test, but something to keep in mind is that when you select a fuse for a large scale battery system, typically it needs a very, very high interrupt current, where we're talking about things that are measured in near 100 kiloamps or around there. And such a fuse is not typically recognized to open at double its trip current. So that basically means the fuse isn't guaranteed to intervene in this test. So as part of the short circuit test, if we were using a fuse, let's say that was 400 amp as its rating, well, double that would be 800. The pre-arcing time, I mean, it's off the graph for how long that would take to open. And during that time, you're having all sorts of components experience significant heating. But by using a BMS that is certified for measuring stack current and using contactors that are rated for the application, this test is over within seconds. So there's no substantial temperature rise. It's just, again, a very trivial test. They kind of set up, they do it, and it's done, and you move on to the next test. But without that recognition and without those contactors, it can be difficult to pass this type of soft short current test. And I did also want to mention one other, maybe not an electrical test perhaps, but it's one that I've been mentioning to since the beginning of this webinar, and that is the single cell failure design tolerance test. And so in an earlier example where that battery stack that uses cells just placed in a metal racking with no thermal separation between cells, the entire battery stack fully populated would have to be evaluated as part of this. So they would actually determine a manner to cause a thermal event in one of those battery cells. And then they would do that with a fully populated stack and see how it propagates. If instead a battery module is used and that battery module has been designed such that it contains the heat energy produced by that cell, then only the module needs to undergo that test. And it's really just to prove that no propagation occurs beyond that. And that allows for a simpler rack design, since the energy to contain within the battery stack enclosure is kept to a minimum. You're not worrying about your entire energy capacity being converted into thermal heat that then has to be contained by your outside enclosure, because each module handles that for you. So I wanted to talk about some of these case studies and also share some of our war stories that we've encountered over the time with our interactions with various NRTLs. And to do that, I'm going to be referencing challenges that we've overcome with our 1973 certification. And these are areas that I think are going to translate well to any sort of UL 1973 candidate rack. So I'm going to be talking about challenges with the BMS, challenges with high voltage wiring. So we're talking about wire that's in excess of 1,000 volts. Fuses and contactors, the challenges around that, as well as the challenge of connectors, how we actually go about installing and connecting the high current path. So we've all been there. And the question that we kind of ask ourselves is, well, what would happen if we just took a battery stack through a 1973 test regardless of subcomponents? You know, as designers, we know that the pack we've built is passing these tests in our lab. And so it's able to meet all of the sort of test criteria around 1973. So let's just take it to an NRTL and have them go through the same tests. And so we have had this experience where that stack did go to an NRTL. It did pass all the tests, but the BMS in it did not yet carry functional safety recognition. So when they got to that point, the BMS was then subjected to single fault testing. And so these photos are actually of a site in the US where you had to go to and actually bring the ability to inject open circuit and short circuit faults within the BMS product and demonstrate that in all conceivable instances, the BMS will fail safely. And so we did this, and it passed all the tests. But what it came down to at the end of the day was a checkbox. The requirement 2.1 and 7.8.1.3, which relate to the components used having to meet their required certification, those were still outstanding. And so as a result, the 1973 stack certification was incomplete. This sort of takeaway is that the component certification checkbox has to be checked off, regardless of how the high-level system performs. It's just an important milestone that just has to get through. And nowadays, it's more. I think mostly this is caught during the construction review phases. But if you really were pushing through and got into the evaluation phase, this is going to be discovered during the report write-up at the end. So example 2 is, okay, so what if the required component certification does not meet your engineering requirements for safe use in the product? So this is kind of flipping it on its head, and it comes into stack design because when selecting a wire for cell voltage sensing, we're going to require a wire that has a small diameter that's compatible with a BMS connector. And we require that wire to still have the voltage insulation rating that meets or exceeds the maximum stack voltage. UL wire today for greater than 1,000 volts typically uses soft rubber, which can be easily stripped using fingernails and can be punctured by cable management clamps and zip ties. So we've actually had a sample of that where you can just grab either end, pull apart gently, and the insulation just slides right off. Or in the middle of a cable, if you do that, you then open it up, exposing the bare conductor. So the interesting part here is that wire technically has UL recognition. So an NRTL reviewer would have found that wire to be satisfactory. But we require a wire that doesn't do that. So it's deemed to be unsafe. And this is by the engineering team, not by the NRTL. And so you get into a position where we need to have a wire that doesn't do that. And the wire that we were able to find, or the engineering team would like to use, doesn't have a UL recognition, but it does have rigorous QC processes implemented by the wiring manufacturer because it is a mil spec and SAE spec cable. And the wire itself has nameplate ratings that far exceed what you'd find in stationary storage. We're talking about wire that can be used in fighter jets or marine applications. And if we're going to be using it in a stationary storage system and in a UPS building somewhere, it's not under the same sort of strain that cable was designed for. So this, we're working with UL here on this specific problem was actually a pretty straightforward process. It definitely had some challenges where we were having to go around with various subject matters at UL about this. It took about 2 months to get to a point where the wire was approved, but we were receiving quotes saying that we had to go take it through UL 758, which would have added 5 months to the schedule. And this is on a wire that really exceeds the minimum requirements, or actually the actual requirements of UL 1973. So there is some flexibility in dealing with these components, but the case is very difficult to make because you have to make sure that the cable that's being evaluated is ensured to have the same characteristics 6 months, 2 years, 5 years from now, if you were to order that same cable. And that's really where those recognition marks come into play, because it just means there's some oversight view. And so in this case, the mil spec and SAE spec could have been used, or has been used, as a substitute. So there's also another aspect that we've run into, which is what if the nameplate rating of a component doesn't match conditions of acceptability, or that the conditions of acceptability are more stringent than that of the component ratings. So we've probably all heard the adage that 3 things can't remain hidden: the sun, the moon, and the truth. Well, as a designer, we encounter 2 truths very often. There's the component operating conditions, and that's declared by the manufacturer, advertised by the sales and marketing department, and does line up with how a device can perform. But there's also the conditions of acceptability, which is going to be stated in an NRTL's report. And the end application that you're using the component in has to satisfy those conditions. So for example, an RU mark here on a fuse means that there are conditions of acceptability to consider. And so you get the report and you look at what are those conditions. In the case of a fuse, it's common. This is not unique to any one fuse manufacturer, that it's only recognized to open between a minimum and maximum interrupting values. And the minimum interrupting value is not usually the same as the trip value. To give an example, not this fuse, but to give an example, a fuse that would be rated to 400 amps and maybe has a maximum breaking current of 100,000 amps would be a good choice for a battery stack that in its typical application is only operating at 75% of that. But according to conditions of acceptability, when we were reviewing it, we could discover that the minimum interrupting value is actually 5,000 amps. And so we need an overcurrent protection device in between to open at 400 amps. A BMS that's recognized to provide that overcurrent protection, if it's been evaluated as part of its functional safety investigation and paired with contactors that are rated for the application, can meet that functionality. And so the moral of this example is, truth number 2 is a critical value for UL 1973 certification. So it's very important to be asking the manufacturer for the conditions of acceptability on any UL recognized component. And this is especially true when it comes to contactors. If the answer from the manufacturer is seeming to be too good to be true, then double check with your NRTL reviewer, because they will have access to those conditions. And also, when it comes to connectors, a question that comes up is it possible to use unrecognized components, that we end up taking through component certifications, right? So for applications that are beyond 1,000 volts or 100 amps, it's hard to find connectors that are available on the market. It's much more common to find unrecognized components for these applications. But these manufacturers of these connectors, they're busy, and so it's not always easy or possible for the manufacturer to invest the time in certifying the component. So if we're going to be using this connector, we need to be prepared to take it through the applicable NRTL evaluation. And there's a bit of a trick here. So because we're not the component manufacturer, we have to gain access to low-level construction and design details. It may also be impractical to implement the necessary follow-up services to ensure that the test results remain applicable. And assuming everything is in agreement, so we were able to get through that, and we're willing to add months to a schedule for increasing cost, then it is possible to make use of an unrecognized component. It just can be significant. So in the example of the high voltage wire, which was one that was near and dear to my heart, because that was quite the scare, going through a 758 review is measured in like quarters. So we're talking about like a 6-month delay. But if that was the only option and we were prepared to do that ahead of time, then it's just part of the schedule, and there is a way through that. I also wanted to mention what it looks like to have parallel stacks. So when using parallel stacks, it seems that we're not going to be required to go through functional safety at a multi-stack controller, and that's correct. So each 1973 battery stack is responsible for protecting the cells. So to explain a bit about that, a multi-stack controller, in addition to aggregating kind of how those individual stacks are performing, it's also going to make decisions about which stack connects to the common DC bus, as well as it's presenting that single interface to a 9540 energy controller. But since the BMS in each stack that's connecting to the DC bus is deciding if it's safe to do so, it's going to prevent an unsafe connection. It also autonomously disconnects from the bus if a fault occurs. And so because of that, the multi-stack controller isn't part of that safety path. Now, it's certainly helpful for higher level controls, so the multi-stack controller or energy management system controllers, to have an understanding of the safe operating range and have its own level of safeguards. But from a certification perspective, that's not required for the protection of the cells. And so by leveraging by leaving the functional safety down at that lower level, these higher level systems can focus on their functions without triggering an unsafe event. So to give an example of like an electric car, if you're going to be pressing on the brake and you're going to potentially lock it up and need your ABS to take over to keep your vehicle safe, you probably don't want that safety function running through your infotainment screen and living on an unrelated piece of the control system. You kind of want to let that infotainment system do its thing and then not have to worry about what's going on with the brake subcontroller. So by separating the 1973 safety functions from a battery control panel, the GUI and the EMS, it's not required to submit that code through a UL 1998 review. This is that multi-stack control. So that allows the multi-stack controller to have product updates that can be built and deployed without adding the delay for a 1973 certification report update. So you can get some pretty user-rich information, make changes to it, and not have to worry about touching a report. And that added visibility and functionality at this high level, we're going to be discussing about that in tutorial number 3. So there'll be more on that later. And I should also be mentioning about in-field customization of a 1973 battery stack, because it's kind of an important part, and I'll explain a bit about that. So as part of a UL 1973 test, the overcharge and over discharge tests require the BMS to open contactors to prevent the cell from exceeding the specifications. That's kind of implied. But in our case, the BMS is fully configurable. So it allows those thresholds to be adjusted as part of development. So we're able to reconfigure a BMS by just uploading a different configuration file, and that will redefine where these limits are. Well, in preparation for a 1973 test, we need to lock those down. And in our case, a CRC is issued. So this is like a hash that relates to what those settings are. And if that value doesn't match what's stated in the 1973 report, then the ultimate stack doesn't have a certification mark anymore. And so this hash value compared to the value that's in your report, that's inspected as part of a production follow-up service, as well as for field evaluations. But even though we've got these two ends locked down and that's part of your technical file, we have a huge range in the middle, and those remain configurable. So to take an example, let's say that that you're comparing it to a PCS, and that PCS might have a voltage window, a minimum voltage, in fact, that it requires the battery stack to be at. Otherwise, it won't be able to charge or discharge that battery stack. Well, if that voltage falls below the minimum of a PCS, it's not possible to recover that in the field without triggering a roll, like a service roll. So you'd have to send out a technician with some sort of charging circuit to boost up the stack. Even though the stack is safe and it's still within its safe range, the site is actually inoperable. And so by allowing those limits to be configured, the BMS can actually send messages out to the high level system and stop itself from getting discharged below what the PCS can do, even though that's not related to the absolute minimum value that the cell supports. This is also useful when we talk about the depth of discharge and minimizing or adjusting the range, so that way you can extend the life of a system. And so we've got a screenshot of a real system here where the PCS had a requirement of 720 volts minimum, but the battery system can go down to 700 easy. And so in this case, even though those safety thresholds might be set there, we're defining our 0% SOC. We're defining our warning zones according to the system. Other examples of where that level of configuration could come in handy would be things around cooling. So for a given site, you might need the fans or your HVAC cooling to be coming in or coming out at different points in the temperature profile to keep all the temperatures nice and tight and on the blue bar. So I wanted to kind of go through a bit of what our services are, what our products are to help enable these types of systems from being built. So we've had multiple battery manufacturers, such as A123, hire us to take their battery stack through a 1973 certification. And we offer these services to anyone as well. So we can do full custom turnkey products that are delivered as an efficient schedule and a ramp rate. So we basically go from your early initial concept to a fully certified, ready to ship product in a pretty efficient time. We can also augment your existing team. And we have established relationships with major NRTLs who can help work through that process. At the end of the day, you will be holding that 1973 certificate and your company name appears in their NRTL database. We're just here to help if you need our assistance, leveraging all of our expertise that we've been picking up over the years. As far as our cell interface goes, a little bit more detail about that for those that are looking to integrate it at the module layer. So this is a module that connects to the battery cells and temperature sensors and provides balancing. It's scalable, so we can manage hundreds of cells in series. It's not a problem. And each individual module monitors either 12, 16 cells in series if they're applicable lithium or 2-volt lead acid or any other under 5-volt cell. We also offer a version that manages monoblocks. So this is our CI 4M12 variant. It talks back through a proprietary link bus to our stack switchgear, and they can perform up to 300 milliamps for CI12 and CI16, and you get 7 temperature sensors. As far as our stack switchgear goes, this is the next level up. So there's 1 per battery stack, and it's going to be combining our UL 1973 battery management modules with additional contactors, fuses. There's a pre-charge circuit inside. And again, we're in the process of getting this all UL recognized at the stack switchgear level. So hunting around for the correct contactor or correct fuse is a task that you wouldn't have to do with our stack switchgear. It's going to be measuring your overall stack voltage and currents. It's controlling the cooling fans or integrating with your e-stop circuit. You can manually disconnect the stack for servicing through the service disconnect switch. And as far as it's the high-end version, so that's 1250 volts and up to 350 amps. So pretty substantial size. And at the multi-stack level, so this is our battery control panel. So this aggregates data and control of multiple stacks. It's going to be communicating with the external controller, or PCS. That external controller doesn't need to worry about how many stacks are in parallel, what are the states of these different stacks. That's all handled by the battery control panel. It's as if it's a single battery that's being presented. So it simplifies that high level control. And included within it, so it does come wall mounted. There is the multi-stack controller inside, in addition to a local UPS, networking hardware, the touchscreen display, and a cellular uplink to notify you if your stack is offline. But if you're not building your own energy storage solution and you're looking for something that's more turnkey, we have relationships with multiple turnkey providers, as shown here. So you can reach out to us for further details if you're interested. These are various stacks that have already integrated our BMSs into them and are available. So we've reached the end of the tutorial number 2. That's now complete. The last tutorial of this series will be on gaining more visibility into your energy storage system, and that'll be hosted on September 9th. So thanks for spending the time with me, listening into what I had to say.